Okay, so let's get started. Today's obviously the last day of class for the course, and we are going to be going over BigO notation, which will in fact be on the final exam. You all did incredibly well on the exam problems yesterday. At least I haven't had a chance to look at them, but there were very few zeros and a whole lot of perfect scores. So looks like you all deserve pats on the back for doing well, especially on the Q problem. I thought that one for sure would be problematic just because it's hard to manipulate pointers and get everything all put together, but it seemed like you managed to successfully navigate through the shoals of that problem. So very pleased. Remember, a week from today, April 30th at 8 o'clock in here, we're having the paper portion of the final exam, and it will be, I haven't made it up yet, but probably somewhere between 7 and 10 problems. Basically, you should expect it to primarily focus on trees because those are where we're going to most easily be able to get questions. Plus, actually, today's lecture on BigO notation is pretty important. One of the big things about this class has been data structures. Okay, so CS 102 is about programming. 140 has been about data structures and how we organize data for efficient retrieval, efficient retrieval, efficient inserting, and efficient deleting, especially when we have variable sized data sets. In 102, we saw your first efficient algorithm, binary search, for finding an element in an array, but the issue was that the array was fixed size. The data set was static. Here, in this course, we've considered variable size data sets. So one thing for sure on the final, so the one thing that perhaps won't be comprehensive or will be comprehensive about the final is I will expect you to be able to compare different data structures. Much like on the first or second midterm, I had some questions where I posed hypothetical problems and asked you what type of data structure to use. You should expect that kind of similar problem on the final, and also you should be able to tell me what are the average case and worst case performance of operations on different data structures. So I will expect you to know, for example, that with hash tables, the average case performance is constant time for insert, delete, and find, but worst case is order n. And same thing for binary search trees. The average case for your finds, deletes, and inserts are order log n, but the worst case is order n. Whereas for AVL trees, both the average case and the worst case is order log n. So I will definitely expect you to be aware of how much time these fundamental operations take on these different data structures, and given a problem, be able to choose the most suitable data structure to use for that problem. And today's lecture on BigO, there will definitely be some problems that ask you to look at a program and figure out what the running time of that program is. If you've looked yet at any of the prep materials for the final, you'll see on Dr. Plank's final exam, he has some problems that are geared toward finding the running time of a program. And then, of course, with the trees, you need to know if I give you a sample tree, you need to be able to insert a node, you need to be able to delete a node, You need to be able to perform the rotate and the rebalancing operations. With B trees, you need to be able to insert. Okay? I'm actually not going to test you over deletion in a B tree. Don't get confused with a binary search tree. I will test you over deletion in binary search trees and AVL trees. It's just what we covered on Tuesday with B trees. Deletes are pretty complicated. I won't test you on that. Inserts are fair game in B trees. Okay? I'm also not going to cover B plus trees in this course. So you're only responsible for knowing B trees. Okay, so questions about that? Yes, Ardalyn? You do not need to know about B plus trees. You do need to know B trees. Okay. Other questions? Okay. So, throughout the rest of your CS career, and even partly in this course, you have seen me, and you'll see other professors, use notation like this to describe the running time of an algorithm. And you'll hear this referred to as BigO notation. Okay, we've already had a brief discussion about it in an earlier class. The purpose of BigO notation is to cut to the chase, so to speak, about the running time of an algorithm. It gets rid of all the smaller parts of the running time, and it gets rid of constants. So for example, if I have the running time of an algorithm that looks like this, okay, where t refers to the time and n the size of the input, which we'll talk about, then we say that t of n is order n squared. And the reason we say order n squared is that we get rid of the so-called lower order terms. We're only concerned with the most expensive term, which in this case is n squared. We also get rid of constants. And so all we're concerned about is the largest factor. So BigO gives us, so BigO notation gives us the running time of an algorithm, the asymptotic running time of the algorithm. Now, we're going to see that there's probably, when we refer to BigO, we typically mean theta O. We'll get to that. But the way it's colloquially used in computer science is BigO notation is typically used to refer to the asymptotic running time of an algorithm as n approaches infinity. Okay, which means the insignificant terms like 4n minus 5 go to 0 in this. They don't go to 0, but when compared with n squared, they get very small. Okay. So, we have a number of issues when we are trying to determine what is the running time of an algorithm. So, the big question is, how do we determine the running time of an algorithm? Because that's the most important. We can't do anything with BigO until we have some idea about how long it takes to run an algorithm. So we could base it on, we could just run it on a computer. So one thing we could try to do is just run it on a computer and see how fast it runs. Okay? But there's some issues with that. First of all, let's say I run an AVL tree algorithm on a computer and it takes 10 seconds. Okay. What questions would you want to ask about that? So it took 10 seconds to run. Okay, what do you think affects the running time, the 10 seconds? What are some factors that might affect it? I tell you that all I did was insert some number of keys into the tree and I timed it and it took 10 seconds. So what are, Doug?
How many times do you were able to insert in those 10 seconds?
So how many times? Okay, so in this case, if I was doing an insert, it would be how many inserts I performed. Okay, what's another factor? You may not think of this one quite so obvious, but can you think of another factor? Mark.
Object creation, structure.
So
That's not tied necessarily to the algorithm running, but it'd be part of the runtime of the program.
it is, although it's probably going to be correlated with how many inserts I perform, because basically object creation will be, I'll probably have one object created for each node. So, yes?
The efficiency of the compiler you're running?
The efficiency of the compiler, yep. So different compilers, the optimizations. So it's not so much how good the compiler is at optimizing the code. So compilers perform optimization. Okay, just as a very simple example, I might have something for I equals, say, 1 to 100. A equals I plus 3 times 100. Okay, this is a very simple optimization, but there's no reason to perform the 3 times 100 every time through the loop. So one very simple optimization is to, at compile time, multiply 3 by 100 and replace the A equals I plus 100 with A equals I plus 300. Now there are much more sophisticated optimizations than this. So that's another one. Okay? I am going to, there's only one more I'm going to put up, and this is a fairly major one. So anyone want to take, I'll give one more guess. Yes?
Processor speed.
Very good. Processor speed. Okay? If I told you it took 10 seconds, then you should want to know, well, was that back in 1980 when it was running on super slow processors, or is this in 2015 when we're running on processors that are, you know, I don't know how much faster they are now, but probably close to several thousand to several 100,000 times faster. Okay, to give you an idea, this isn't processor speed, but in terms of miniaturization and cost. So the first transistors, a single transistor, does anyone know how much a single transistor first cost? $150 for a single transistor in the 1960s. Okay. Today, 70,000 transistors cost 1 cent. Okay. So speed is probably roughly comparable to that. Okay, so you have several thousand times speed up. So processor speed is important. So what I'm trying to get at here is that there are certain things beyond our control when we run this, which is processor speed and how good the compiler is. But the number of inserts I perform, that's something we can get our hands on. So when we're looking for determining the running time of an algorithm, we typically have a pretty intuitive idea that the size of the input is probably going to affect the running time of our algorithm, with larger inputs intuitively taking more time to process than smaller inputs. So typically, we try to express our running times as a function of the size of the input. So often express running times as a function of the size of the input. And typically, we call that n. Okay, so we say the size of the input is n. Just an idiom that has been adopted by computer scientists through the decades. Okay, so in this case, the number of inserts I perform is going to be probably 1-to-1 with the size of the input. So the next thing I have to do is say, how am I going to count things? And typically, what we're going to do is count instructions. Okay, so typically we express running times, or we express running times as a count of the number of instructions executed. So if I say t of n, so t of n refers to time. So this is time. So the time to process n, say, input items, I might say n squared plus 4n minus 5. What I'm saying is that if n is, say, 10, I expect to execute 100 plus 40 minus 5, or 135 instructions. Now again, we generalize. We're going to assume that each instruction executed takes the same amount of time. In a real computer, this is not quite true. If I say 3 times 6 and 3 plus 6, the plus operation executes faster than the multiplication operation. So it is, in fact, not the case that every instruction takes the same amount of time. However, the instructions, for the most part, are within a constant amount of time of each other. Okay, so it's not like one instruction takes n times longer than another instruction. They're within a constant. So maybe the multiplication takes 5 times longer than the addition. We're willing to live with that. Okay, so we just assume that the instructions take a constant amount of time, and that we count each instruction as 1. Okay. It's pretty much not possible to get an exact count on the number of instructions. We're simply going for a good rough measure. Okay, so we're not going to get bogged down in trying. So this is way too, this is way too specific, as it turns out. Okay, we're never going to come to this really to something this precise. It's just an example. Okay, so our assumptions, very important. We will assume that each instruction takes a constant amount of time. Okay, and we'll assume that all instructions take the same amount of time, even though we know that's not true. So we're abstracting away from the processor speed. Okay, we're just counting instructions. We're not trying to figure out how much time each instruction takes to actually execute on, say, an Intel chip or a PowerPC chip or anything else. We're just saying each instruction takes the same amount of time. Okay? There's a few very basic rules for counting the number of instructions. Okay? So, rules for counting instructions. Okay, so rule 1, pretty obvious. If you have two sequences, so if you have two linear, by which we mean no control loops or anything else, if you have two linear sequences of code that take A and B time respectively, then together they take A plus B time. But more importantly, they take a constant amount of time to execute. If they're just simple instructions. Actually, I'm going to not. You could have a function. Well, I did say no function calls. So we do say. So they take constant amount of time. So that should be pretty intuitive. If I just have two linear pieces of code, like say x equals 3 times b, y equals z plus b, and then I maybe have a loop, which we haven't done yet, and then after the loop I have, say, cout result, return 0. Then I would say this is one instruction, this is one instruction, this is one instruction, so it's 2, this is 2, 2 plus 2 is 4. Okay, so a very simple thing. Two linear sequences, you add them together. Okay, linear sequences without control structures embedded in them, like function calls, loops, if then else's, they take a constant amount of time. Okay, second thing is how you count instructions in loops. Okay, so cost of a loop, or running time, say running time of a loop, is equal to the number of iterations times instructions per iteration. Makes sense, right? If you have a for loop that looks like this, for I equals 0, I less than 10, I plus plus, say sum equals sum plus I, C out sum. Okay, how many times does this execute? 20?
Oh.
Okay. Oh, how many iterations? Sorry. 10 iterations. Okay, now counting loop instructions is always a little bit of a misnomer. So it sure looks like, so we have a linear sequence here, right? Okay, and we're going to count, even though cout is a function, we count it as taking one instruction. So we're going to say there's 2 instructions there. Okay, can anyone tell me, there are a few more instructions being executed though. What are some other, that's right, so the comparison and what else? And the increment. So in fact, not only are the 2 instructions obvious in the loop body executed, but each time there's a comparison operation and an increment operation. So in fact, there's 4 operations total in this loop, and the number of instructions is roughly 40. And then we didn't count this. This actually is before the loop, but that initialization is actually 1 additional instruction, but we count it as being before the loop. So technically, this one is taking 41 instructions. Again, you know, you could start to quibble and say maybe there's some other things going on. Sure. Okay. If someone's doing a strict analysis of this, they would realize that the comparison is performed how many times? 11, not 10. So that's why we don't get bogged down in trying to get it exactly right. Okay, so it's really 10 times 4 plus the 1 extra one for this plus the 1 for this. But we don't get bogged down in those small details. That's just change, small change. It's like pennies. Okay, and they just don't add up. Okay, so that's why we don't get bogged down trying to get an exact count. Here, it probably would be good enough to just say, well, it's roughly 2 times n. Okay, I'd prefer 4 times, but 2 times would work too. But the critical thing is you count iterations, multiply it by the number of instructions per iteration. So questions about that? Okay. So next one is, what happens if we have if-then-else statements? Okay. Well, we have to be pessimistic. We don't know in advance which branch of the if-then-else is going to execute. So we count the time of an if-then-else as so we say the running time equals the running time of the comparison. And does anyone want to take a guess at how we're going to get the rest of it?
Plus the running time of the longest condition.
Very good. Plus the running time of the more expensive condition. I'll call it branch. Okay, so if we have if A less than B, then for I equals 1 to 100, ... else print A, the cost of the comparison is 1, the cost of the else is 1, the cost of here, let's say there's 2 instructions in here, is roughly 4n, what we've just seen, or 4 times 100. So this is definitely 4 times 100. So we would say that this if then else costs 1 plus 400 because the if branch is the longer running of the two. So we have to take a pessimistic outlook because what we're trying to do is put an upper bound on the running time of the program. We're not trying to put a lower bound on it. So we have to be pessimistic and assume that we're going to always execute the more expensive branch. Okay, if you have information that, for example, you know for a fact that each branch executes exactly 50% of the time, then you could apply that information. But in general, we do not know that, and so we have to be pessimistic. Okay, questions about that? Pretty intuitive, right? Okay. 4. Okay. Is what happens when we have nested loops. Okay, so we have 4, I equals, say, 0 to 100. 4, j equals, say, 0 to 1,000. How do we cope with nested loops? And the answer is that we do our computations inside out. So we start with the innermost loop and work our way out. Okay? So start by computing running time of innermost loop and work our way out to the outermost loop. Okay, so if we have 4 I equals, say, 1 to n, 4 j equals 1 to m, 4 k equals 1 to, I don't know, w. We would first, and it does some stuff, we would first calculate the running time of the loop involving k. Let's say it was 2 times w. Okay, so now we would say, okay, we'll know that we can get rid of this innermost loop, and we know that that loop takes 2 times w time. Okay, now we can compute what this loop is. Well, it runs m times. So each iteration takes 2 times w instructions. It runs m iterations, so that's 2 times wm. So now we replace this loop, and it is 2 times wm. And finally, the outer loop executes n times. Each time it's 2 times wm equals, m equals 2 times w times m times n. So we now have the total running time is that. So it's just working our way from the innermost loop to the outermost loop. Okay. Now, it's not always quite so easy. We might have 4 I equals 1 to n, 4 j equals 1 to I. Now it's a variable number of instruction or iterations in the innermost loop, and it depends on I. Okay, so each time through, let's say there's 2 instructions here, okay, plus the 2 we just figured out earlier, so let's say it's 4 times I. Well, that's a little harder to work out, right? Because i's going from 1 to n. There's two ways we can tackle this problem. Okay, one is we can choose to be super pessimistic and say, well, we're going to take the maximum value for I. Okay, we're going to assume in each iteration the worst possible case. So the easy way is just to always use the maximum value for I. So always use max value for I. Okay, in that case, what's the maximum value for I? N. So in the worst case, J is taking 4n instructions, and the outer loop is executing n times, so we would come to 4n squared. So we know that's very pessimistic. Okay, that might be looser than what we're willing to accept. So we could also realize, okay, what we have is the first time through, it is 4 times 1 plus 4 times 2 for the second one, plus 4 times 3 plus ... plus 4 times n. So the values of I go from 1, 2, 3, 4. So that's equal to 4 times 1 plus 2 plus 3 plus ... n. Has anyone seen the solution to that sequence before? I know someone has. May not be able to remember it though, right? Yep, it's n times n plus 1 over 2. It's the solution to this. Okay, I'm not going to go through it. You'll just have to take my word for it. Okay, so doing the cancellation here, we get 2, so it's really 2 times n plus 1. So it's really 2n squared plus 2n. Okay, so we realize that in fact, if we do it a little more closely, it's about half of what we came up with for the pessimistic one. Now, do we really care in the long run? No, because remember, BigO notation is going to get rid of the constants. So in the long run, it doesn't matter whether we choose case 1 or case 2, because the BigO notation doesn't care about the constants. So in the long run, BigO notation says, well, we don't care about that. We don't care about this, and we don't care about this. Voila, either analysis gives us n squared. So we're typically a bit lazy in this case, and we make a pessimistic assumption because we know in the long run, as it's asymptotic, shouldn't say in the long run, but asymptotically, it doesn't matter which assumption we make, we're coming to n squared either way. Okay, and I'd be fine with this on a test. Although you have to be sure of this calculation. Okay, so questions about that. Okay, and the final thing is if you have a function, because functions are the last control structure. So if a sequence of instructions involves a function call, then you replace the function with its running time, or you use the running time, then you use the running time of the function call rather than assuming it takes one instruction. So you don't assume that a function call takes one instruction. You have to compute the running time of the function. Now, I remember back here was cout or print. In both cases, I explicitly made the assumption that cout takes one instruction. Well, that's probably not really true, but I do know that cout takes a constant amount of time, so that's good enough. If we know that a function takes a constant amount of time, we typically would just replace it with a constant c. But sometimes that function is doing something. Like if I ask you to calculate, if I have main, okay, and I do cn into n, okay, cout gets factorial of n, it is not right to say that the running time of this thing is 2 instructions, because we pretty much know that factorial of n takes order n time to compute. So we in fact would have to say that the cost of this instruction right here is not 1 but n. So we have really 1 plus n as the running time. So bottom line, if you have a function call, you can't assume the function call takes one instruction. Now, we often assume that things like a read or a print take a single instruction. What we're really saying is we know they take a constant amount of time to execute, and as long as it's constant, we're good. It's not a function of the size of the input. Okay? You might say, well, wait a minute. It is a function of the number of things I have here. So if I have n, I, phone, but nonetheless, there's a limit to how many things you can put there. Okay, it's ultimately a constant. No matter how many you write there, by the time you get around to compiling the code, you could only put a constant number of variables after your cn. So we still count it as constant. This is why I say we're never going to get an exact count on the number of instructions. Okay, so we just make general assumptions like a read statement takes one instruction, a print statement takes one instruction. Okay, so we're just trying to get rough estimates. Now, in fact, if we're trying, we don't even typically go to this much trouble to try to get a t of n. Because given all that, you've just seen that at best we're going to get rough numbers. We're going to roughly get a of n squared plus, say, b of n plus c. And there's going to be a lot of give in these constants a, b, and c. What we're really trying to get at is what is the big number there. Okay, is it n squared? Is it n? Okay, in the case of the Fibonacci sequence, when you're doing fib of n equals fib of n minus 1 plus fib of n minus 2, it actually gets a lot more complicated. Okay, we actually have to start solving a recurrence, which is not so easy to do. Okay, but it turns out that that one is exponential, that running time, I forget exactly what it is. Shoot, I saw it the other day, and now I've... But it's exponential, I know that. So it's on the order of 2 to the n. It's actually worse than that. But that's a horrible one. 2 to the n grows much, much faster than n squared, or any polynomial. Okay, and you're going to learn in 302 that there is a class of problems for which it's hypothesized that the best possible algorithm is exponential. And that no matter how fast we make our computers, you will never be able to rapidly solve an exponential problem. Okay, remember Moore's law doubling every 18 months? What does that mean in the context of 2 to the n? It means that every 18 months we'll be able to solve a problem one greater than the previous one in the same amount of time. So if it used to take, say, 10 minutes to solve a problem with 2 to the 100th number of elements, in 18 months when we double it, we can now solve a problem with 101 elements in 10 minutes. Okay, exponentials are horrible. Okay, they completely blow away Moore's law. Okay? No matter how fast we ever make our computers, we will never be able to efficiently solve exponential problems. We hate them. Okay, so we're always trying to find solutions that take a polynomial amount of time. There is one last thing. So we're not really going to consider it that much in this course. But you will find that when you go to 302, that sometimes these counts aren't as easy as what we've done here. This was one of them, where you come up with this kind of recurrence relation. Okay? You'll find in 302 that there are algorithms that are like that as well. Okay? A popular sorting algorithm, okay, is to take an array, essentially divide it in half, sort each half, and then merge the two sorted halves. Okay, and it can be shown that the running time of such an algorithm, well, at each step you're sorting two halves, so it's 2 times t of n divided by 2 because you're sorting two halves, plus the time to merge them together, which is n, roughly speaking, because there's n elements in the array. You have to solve that. Well, mathematicians have done it. It can be shown the solution to that recurrence is n log n. But we're not going to do it in this course. I'm just saying a more advanced concept is that you can end up with these types of recurrence relations and having to solve recurrence relations. Okay, we won't consider that in this course. Okay, so looking at Dr. Planck's notes now with that lead-in, he shows us a program. Can you read it in the back? Okay, if you look at this, you should be able to scan it, and you can see that most of them are taking a single instruction, right? Single instruction, single instruction, single instruction, single instruction. But the for loop is not. Okay, the for loop is taking how many iterations? N. And the loop body, there's roughly 1, 2, 3. The printf is counted out. I'm sorry, the count. So there's roughly 4. Plus there's the 2 right here. But really, looking at this whole algorithm, we don't even have to go into that much detail. We can tell that the most expensive thing in this entire program is this loop. This loop takes n iterations, and therefore it's going to be an order n running time. Okay, so usually we just end up eyeballing our programs because it's the loops that typically determine the running time of our programs. That's what it comes down to. Loops are what determine the running times of our program. If there are no loops in our program, what do you think the running time of the program is? No loops. C, it's a constant. So if there's no loops, well, and no recursion. Okay, if no loops and no recursion. Okay, then running time is what we call order 1, because again, we don't care, we collapse all constants to 1. So you'd never see us express the running time of a constant time operation as order C. It's always expressed as order 1 to indicate its constant time. Okay, so really what we do is we're just looking at the running times of the loops and of recursion. We have to look at recursion. It's actually, when I talked about this kind of recursion or recurrence relation, it comes about through recursion. Okay, so these nasty recurrence relations come about as a result of recursion. Okay, we're not considering them in this course. That's for 302. And for 311 when you take 311. Okay, also in this one case, we actually pessimistically, just once I'll get to you, Samantha. In this one case, we would pessimistically assume the cost of this if then else to be 1 rather than 3. Why would we actually pessimistically estimate it to be 1 rather than 3?
Because
It exits. If it exits, then the program's a pretty cheap program. Okay, it never gets to the loop. So this would be a special case where we have some knowledge about what's in that if then else. There's an exit statement there. The exit statement gets executed. Program doesn't run any further. So in this case, we'd probably actually, and this is an advanced concept, don't worry, I know if someone looking later at these notes might think, wait a minute, that exit introduces some interesting complications. Indeed it does. Okay? We would actually estimate the cost of that if then else at a single instruction, because if the body executes, we're done. Okay. So, Dr. Planck then shows you, well, he does some running times, and as you expect, the bigger the size of the input, the more time it takes to run the program. Okay, and then he shows you a number of different programs that this one has 2 consecutive loops. Okay, each loop you can see takes n iterations. So this one is some constant a times n plus some constant b times n, which is equal to a plus b times n, which gives us order n. Okay, so that's an example of combining the sequence rule, which was rule 1, with the loop rule. Okay? This one is n squared because we apply the innermost, we first look at the innermost loop, which is taking n iterations times some number of instructions per iteration. Then the outer loop, so once we have that, we know the inner loop is an. The outer loop executes n times. So we have an squared, so that gives us a order n squared for this one. The other 2 require a little more sophisticated knowledge of math. So here, this loop is I is being doubled each time. And you can't, in this case, make the pessimistic assumption that the loop executes n times, because I is doubling each time. It turns out that if I doubles each time, the loop executes log 2 of n times. I'm not going to go through the proof, but that's what it is. That's the definition of a logarithm. So, with pardon?
If it was tripling each time, would be log
3. Very good, Gerald. So Gerald's question was if it was instead I times equals 3, then in fact it would be log 3 of n. Okay. This is a much better loop, as we'll see in a moment, in terms of running time. And finally, this one right here, the inner loop is doubling I each time, so it's running log 2n times some constant a. So the inner loop is taking a log 2n. The outer loop executes n times. So we multiply this by n, and we come up with order n log 2 of n. So you see, loops are dominating everything. It's essentially, we are figuring out how many iterations the loops take. They dominate everything else. Everything else is essentially a constant, as long as it's not a function. Yes, Doug?
Are recursive calls linear?
No, that's where we got this nasty recurrence relation from, where we were dividing the problem in half each time. So each problem had a input, each half, since we divided in half, it was n divided by 2. There were 2 halves, so we were calling the recursive function twice. And then when it came back, we have a merge where if this is, say, 1, 5, 7, 8, 9 after it's sorted, and this is 2, 4, 6, 10, 11, 12, we have to go through each half and merge them together. So this is order n work. Okay, so no, recursion isn't linear. You actually have to break it down something like this into a recurrence relationship. We won't worry about analyzing recursion. We will only worry, guarantee this for the exam, we will only worry about counting loop iterations, essentially. Okay. Okay. And if I just have so what he didn't show was if I just have a program main, and it's like cin n, cout n, cout n equals n. Okay, there's no loop in this one, so we say its running time is order 1, or constant time. So any operation that doesn't involve a loop or recursion essentially is a constant time operation. Okay, so when we try to access the element of an array, that's a constant time operation. It takes a constant amount of time to access an element in an array or a vector. When we say that it's order 1 time to do a find in a hash table on average, if you think about the operations in a hash table, it calculates the hash function, which we typically assume is constant time. That key is used to find an entry in an array. That's constant time. And if we're using, we assume for example, if we're using separate chaining, that the number of entries in each bucket is constant. Therefore, we only have to look at a constant number of entries, and therefore the whole thing is a constant time operation. Okay? But in the worst case, all n keys end up in the same bucket. In that case, we have to search the entire list, and since there's n items in the list, in the worst case, it's order n. Because in the worst case, all n keys end up in the same bucket. But on average, if our hash table is big enough, we only have a constant number of keys in each bucket. Okay, so questions about any of this? Okay. So taking a look at the different running times, Dr. Planck graphed them. Okay, and what you can see, log, sitting there on the axis, never seeming to move above 0. Okay, this is a log, this is on a log, no this isn't, this is a regular thing. We see n squared going straight up. It's horrible. Okay, linear and a second linear. So the two linear ones kind of in between. So it's kind of hard from that to get an idea other than log n really good, n squared seems to be pretty bad. So here he blows it up a little. In fact, here he shows the computation, which you should be able to work out yourself. Log n is better than linear, n is better than 2n, 2n is better than n log n, which is better than n squared. So here he breaks it out by timing some things, and he includes an n log n. And again, you can see the bottom, the red still hugging. The n log n isn't horrible. The n squared is still horrible. Okay? And this, I believe, is just 10 million, and I think this may have been 100 million. Am I right about that? Or 1, 2, 3, 4, 5, 6. Yep, this was 100 million. He's blown it up here, believe it or not. This is 10 million. Okay, but the log n is still hugging the line. So here, well, he hasn't. So here he's at least tried to show what n squared does, because n squared is always going straight up the vertical axis. He's only able to get to 15,000, and you're already up to 150 seconds. So with 15,000 elements, even on a very fast processor, this was probably about a year or two ago, his program took 2.5 minutes. And he obviously never bothered to get up to these bigger numbers because he would have been waiting an awfully long time, probably a matter of hours or days. So even n squared isn't particularly good. N log n is typically the highest that we're really happy with. Okay, although there's certainly things like matrix multiplication where you can't do a whole lot better than n squared. That's not true. Yeah, matrix multiplication is n squared, and then some of the algorithms on matrices can go up as high as n cubed. Okay, so I'm going to move. I don't really care about these functions. You should be able to pretty much get rid of the constants now. So now on to the mathematical, the heavy math part of today, which you at least should see. Okay, so the takeaways thus far is we're using BigO to compare two algorithms. If one takes n squared and one takes order n, we typically prefer the one that takes order n. Okay? That's why we're saying with hash tables, when I say all I have to do is do find, insert, and delete, and I ask you which do you prefer, a hash table, a list, or a tree, I expect you to say a hash table because on average, a hash table takes constant time to do its operations. A list takes order n time, at least for find and delete, and a tree takes log n time. So among these three, the hash table wins. If I now say that the items have to be kept in sorted order, I can't use a hash table anymore because a hash table insists on randomizing the elements. I can still use a list and a tree, but now the tree becomes my favorite because log n is better than order n. Okay, so that's why it's important to know the BigO running times of the different algorithms, because it allows you to asymptotically compare algorithms and decide which is faster. And in general, we prefer the faster one. And of course, you'll say, well, Brad, what happens if I have two order n algorithms? What then, smart Alec? Well, constants become important. Okay, so then we have to know if this one is 3n and this one is 10n, clearly we prefer this one. So at some point when we have two algorithms that asymptotically take the same amount of time, constants in fact do become important, and we have to start counting them. Okay, also constants do count in practice. That's why sometimes I harp on, why on your tests I will say this is an unnecessary statement, because even though in the abstract case we don't care about that extra statement, in practice we would prefer that your program run faster than slower. So in general, yes, I want there to be fewer statements in your program, even if asymptotically I prefer this program, even if this one asymptotically seems to be the same. Okay, on to the math part of today's talk. There are actually three concepts, and of course I can't draw my Greek letters to save myself. Theta, so this is called BigO, this is called omega, and this is called theta. Okay, so let's graph our function t of n. Our function t of n squiggles around like that. Okay? What we're going to find is we want to be able to find out something that at some point, actually don't do it this way, do it this way, and let's use red. Something that at some point x0, the function O of n becomes always greater than t of n. For any value x greater than x0, if we graph it, O of n is greater than t of n. And omega is going to be something where, whoops, it's not going to go down. It's going to go up. Darn it. But it's not going to rise as fast. So at some other point, okay, say x1, for all x greater than x1, we're going to have that the omega function is less than t of n. So for all x greater than x0, O of n is greater than t of n. For all x greater than x1, omega n is less than t of n. So basically, omega is a lower bound on t of n's time, and O of n is an upper bound on t of n's time. Okay, theta is something that is a tight bound. So it turns out that O of n can be a loose bound. So if I have T of n equals 3n plus 1, T of n is order n, but by my definition, it's also order n squared, because n squared for any value greater than 4, so for x greater than or equal to 4, n squared is greater than 3n plus 1. So order n can be a loose upper bound. What we want is a tight bound. So theta is our tight bound on it. Okay, so it's a tight bound. So I'll just for a moment say tight upper and lower bound. In fact, when we say that an algorithm T of n is order n, what we actually typically mean is that it's theta n, meaning it neither runs more slowly than order n, nor does it run faster. But we're lazy in computer science, and we typically say big O rather than big theta. Okay, so here are the definitions, prepared to be dazzled. Okay, so nice mathematical definitions. So if f of n is order T of n, then what we're saying is that T of n is bigger than f of n. So what we're saying here is that T of n is bigger than f of n for some x greater than x0 and some constant t. Okay, so at some point c times T of n is greater than f of n for all x greater than x0 and some constant t, c of T of n is greater than f of n. Therefore, that's f of n is a lower bound, and we say that T of n is big omega f of n. Okay? And big theta says if T of n is equal to order f of n and T of n is equal to omega f of n, that's a tight bound now. So it's f of n is both the upper and lower bound, therefore it is a precise bound for the running time. So big theta is the most precise specification. Big O can be a loose upper bound. Omega n can be a loose lower bound. So for example, if I have an algorithm T of n equals 3n plus 1, T of n is omega order 1, it's omega order log n, but that's pretty useless to us. Okay, those are too loose. It's also, most importantly, omega n, and because T of n is also big O of n, the two of these together imply that it's theta of n, and that's what we want. So we're looking, when we say big O, we're really talking about the tightest bound that we can get. Okay? So on the exam, just quickly, because we are, let me just go through the rest of his notes so you don't get too concerned. Sure, look at his big O stuff, but look, this is what I consider important when you're studying for the exam. make sure that you kind of look through using BigO to categorize. This is just a summary of what we discussed all semester, okay? But want you to be up to date with like what operations are order 1 in a list or a DQ, what are order log n. Finally, if you're wondering what kind of order n questions I might ask, if you go to exams, you look at Dr. Plank's Spring 2014 final. Okay, there it is. Question 1, BigO. Okay, so go through Dr. Plank's exam and you will see some BigO questions on it. Make sure that you can answer those BigO questions. Mine will be the same. I may also give you programs. Okay, kind of like what he did here. Code analysis, question 4. I might give you programs and ask you to analyze them. Tell me what their BigO is. Or if I give you something here like he did, 10 seconds, 11 seconds, 20 seconds, and I ask you, I say, this one program takes 10 seconds. What would I expect if I doubled the size of n? You should be able to tell me how long the program should run. If it's n squared, and n takes a second. So if I know that on a program of size n, it takes n seconds, I know my algorithm is order t of n is n squared. If I double n, it becomes 4n squared. So it's taking, if n takes 10 seconds, 2n is going to take 40 seconds. Okay, because n took n squared time, 2n takes 4n squared, or 4 times as much time as n. So I'd expect you to answer 40 seconds in that case. Okay? So I will see you all Thursday, a week from today. Good luck on the rest of your exams and on wrapping up the courses.
For your exam, can you slide that again?
Yeah.